before we begin, I just want us to reflect. What are we going to do to make the world a better place today? We're here to share our experience, to communicate and to collaborate. And we're thankful for this opportunity to improve our understanding as a team and to build a solution that's going to help cancer patients all around the world. And with that being said, I'll let Adam take the microphone away. And remember, everyone is welcome to type any questions that they have while he's presenting. We'll have a few pauses to address these questions and then also question and discussion at the end.
Okay, thank you very much, Ben. So I'm actually presenting the first presentation for my colleague Claire Dempsey, who gave an earlier presentation. So she made a presentation about forward-stepping applicators and commissioning of rings. So this will be of importance especially to nucleotron users. And then upon completion of this presentation, I'll begin my own presentation on backward-stepping rings. So Claire was nice enough to create a presentation and create voiceovers. So I'm just basically going to play her presentation. If you all have questions, of course, I'll be happy to answer those as well. So I will go ahead and begin.
Hi, I'm Claire Dempsey, and this presentation is to explain how the radioactive source position varies forward-stepping type HDR afterloader, particularly when the source is travelling around a ring applicator. Hi, I'm Claire Dempsey. Nucleotron or Elector HDR afterloaders tend to use a forward-stepping treatment technique. This is where the source will start at the most proximal dwell position and then step forward in the applicator at each individual dwell position. Use a backward stepping source treatment technique, where the source is driven to the furthest dwell position and then the source steps backwards in the applicator towards the afterloader. If you click on the video on this slide, you'll see an example of what a forward stepping source will do. So why does it even matter whether a source is stepping forwards or backwards inside the applicator during treatment? In the majority of cases, it makes absolutely no difference and won't affect the way you plan or treat the patient. The only real exception to this is if you're using a ring-style applicator. But why is the ring applicator different from all the other types of treatment applicators? In other applicators, the source travels along the central path or the centre of the inner lumen, and the step sizes of the dwell positions are equal. So it doesn't matter whether the source is forward stepping, like in a Lecter or nucleotron machine, or backward stepping, like a variant or Bebic type afterloader. When we use a ring applicator, the source doesn't travel along the central path with equal step sizes. This is due to a number of reasons. The inner lumen or inner channel of the ring applicator is generally wider than usual. This enables the source and the cable to move easily through the applicator without causing an obstruction interlock if the source touches the edge of the applicator. Friction between the source cable and the inner lumen also differs in different parts of the ring as the source travels through it. The tension on the source cable also changes as the source moves around the ring. In a ring applicator, this variation in source position will also depend on whether the source is stepping forwards or backwards through the ring applicator. To better understand what happens with a forward stepping source afterloader and a ring applicator, let's quickly refresh on what happens with a backward stepping source afterloader and the ring applicator. In these cases, the source is initially driven all the way to the end of the ring. To retract the source back around the ring, firstly, the source cable must straighten and tighten the wire around the ring. So this will appear as the first few millimetres of source cable retraction, and the source won't actually move physically inside the ring. Once the source cable is tight enough, the source starts moving in the ring, and the stepping motion is generally uniform with equally spaced dwell positions. To correct for this in the treatment planning system, you can define the end of the ring channel beyond the physical end of the real channel, and then apply a source offset in treatment plan.
Okay, again, this will be covered in detail in my presentation. Claire is just giving a brief overview now of the backward stepping.
So what happens with a forward stepping source in a ring afterloader? As the source steps into the ring, it tends to travel in a straight line until it hits the side of the inner lumen. The source then slides along the edge of the inner lumen around the outside of the ring. Around about halfway around the ring, you'll see the source cable will kick out, and this means that the source will move very little over several source steps. The source is then pushed by the cable around the edge of the inner lumen to its most distal dwell position. This top picture is a video that was taken using a ring applicator and a microselectron afterloader. If you click on the image, the movie loop should start playing. What you'll see is exactly what was just explained in the previous slide. The source moves in a straight path until it hits the side of the lumen. It then scoots around the outer edge of the lumen until it gets to about halfway around the ring. At that point, you'll see the cable will kick out onto the outer edge of the lumen, and for several dwell positions, the source won't physically be moving. You'll then see the source continue its motion around to its most distal dwell. This slide, a couple of still images that shows you the straight path motion at the beginning of it. And then the pictures on the bottom right show how the source is not moving over several dwell positions, and that the source cable moves from the inner part of the lumen to the outer part of the lumen over several dwell positions. So is this source motion the same for every single ring applicator and every single afterloader? The exact motion of the source inside the ring is dependent on a number of different things. The first one being the size of the ring. Obviously, a smaller ring will have a tighter circle that the source needs to travel around. You can see in this image the difference in the source path, which is the red dotted lines, compared to the central path of the inner lumen, which is the blue dotted lines. These images show the initial straight path of the source as it travels around the ring, and then at the bottom edge of the ring, you'll see a lot of red dots joined close together, where the source is not moving over several different dwell positions. You can also see that the diameter of the ring can also affect how far towards the end of the ring the source can travel. The motion of the source inside the ring can also even depend on what the ring is made from. In this slide, you can see X-ray images of a source travelling through a plastic style ring applicator, as well as a metal style ring applicator. In the plastic ring applicator, the source tends to run along the superior edge of the lumen, whereas in a plastic ring, the source tends to travel much more central, almost following the central source path inside the metal ring. You can see that the plastic ring has almost a U-shaped channel for the source to travel in, whereas the metal ring has a very spherical type channel for the source to travel in. And this is part of the reason why the source behaves differently in different types of applicators. Another thing that the motion of the source is dependent on is the source itself, the afterloader used, and the step size chosen for the treatment. In this slide, we can see the different source paths taken for a flexitron system with a 1 mm step size and a microselectron system for a 2.5 mm step size. You can see in the flexitron system, at the bottom of the ring, there are multiple dwell positions on top of each other, whereas in the microselectron system, the dwell positions appear to be much more uniformly spaced. So there is an impact on step size and source type that will affect how the source moves inside the ring. We're aware that the source travels differently through a ring applicator than other types of applicators. We need to find out how we can correct for this source position, both in the treatment planning system and treatment afterloader for patient treatment. Electa have what's called an applicator library. This is a library of every available applicator within the Electa nucleotron system and consists of full 3D dimensions, the outside and inside of each applicator, as well as the source path that the source takes as it moves through the applicators, including the positions of each individual dwell position. Unfortunately, at the moment, to have an applicator library within the HDR Brachytherapy planning system, you need to purchase a separate license to do this.
I'll just point out now, if anyone does not have the license, you should talk with Ben, myself, and Claire, and we can do our best to get that license donated for you through our organizations and by Electa. So if you don't have it, it's very helpful, so talk to us and we can try and get it donated for you.
If we don't have the Electa applicator library or the correct model of the ring applicator that you want to use in the clinic for treatment, this is a much more difficult and complex process. This is because even if you manually reconstruct the correct source path, the difference in the source spacing will mean that your source positions will be wrong in the treatment plan. This is because each separate dwell position is not equally spaced from each other in reality. The image you can see, the bottom left corner, you can see the applicator model source positions are in the red dots. These are physically correct positions that the source dwell positions would be at. In the same image, you can see manually reconstructed source positions in pink. This is for the exact same source path and the exact same dwell positions. You can see because the dwell positions in the manually reconstructed source path are equally spaced from each other, and in reality they are not equally spaced. As you go around the ring, the differences between the physically correct position and the reconstructed position get bigger and bigger. So how can you go about fixing the discrepancy between the physically correct source positions and the manually reconstructed source positions? You could try using a single offset value in the same way that you use for a backward stepping HDR afterloader. Unfortunately, this won't perfectly correct for the right source positions. You can see the images in this slide. We've chosen different offset values to see if we could get a better match between our physically correct source positions and our manually reconstructed source positions. The red dots are our physically correct, clinically relevant source positions, and the pink dots are again the source positions provided for the same dwell position in a manually reconstructed system. Even by changing the offset values, it's not possible to get a perfect match between what was a physically correct dwell position and a manually reconstructed dwell position. Really, the only way you can fix the problem of incorrect dwell positions without an applicator model is during applicator commissioning. So as part of the applicator commissioning process, you need to determine the actual dwell positions that correspond to the clinical dwell positions you're going to need for your patient treatments. So this is what you need to put in a plan that is used on the treatment afterloader. However, you will then need to create a separate plan to determine the approximate dwell positions in the treatment planning system that correspond to the actual dwell positions you need on the treatment afterloader. This is required so that you have an accurate dosimetry display in the treatment planning system for evaluation of the treatment plan itself. This is really not an intuitive process and can be very, very difficult. And I highly suggest that this is not something that you attempt to do in your department. So as part of applicator commissioning, particularly for a ring applicator, not only is it important that we determine the distance from the inner lumen of the applicator to the very first dwell position, but we also need to determine what the clinically relevant dwell positions are going to be for our patients using this applicator.
Okay, so this is different than most of our applicators. So all of our other applicators, you find the offset with that first sentence to determine the distance from the inner lumen to the first dwell position, or however you commission your offset. It could be from the outer edge of an applicator to that first dwell position, but it's all based on the first dwell position. And that's for all of our other applicators, all the dwell positions move the same spacing as is in the TPS, not for the ring.
So if you don't have an applicator model, an applicator library system provided, and you really want to accurately the patient with the first plan will have an accurately displayed dosimetry within the planning system. So the doses that you see on the screen of the planning system are going to look right. However, you're going to have the wrong dwell positions activated in this plan. You're then going to have a second plan that has the right dwell positions that are required for treatment. These are the dwell positions that you've determined during applicator commissioning with your film and your images. However, when you look at those dwell positions in the treatment planning system, the dosimetry isn't going to be correct, because in the treatment planning system, those dwell positions are going to be in the wrong position. It's a very, very confusing system, which is why, again, I really highly suggest that this is not how you attempt to plan ring applicators. I would really suggest that if you don't have the applicator model for a ring system, that you avoid using the ring system altogether.
Okay, so the top picture has been manually reconstructed without the library applicator model. And so it looks good on the planning system, but it will not be delivered correctly inside the patient. The bottom one, Claire has used the offsets determined for each individual dwell position and has determined the correct dwell positions to put in the plan so that it does look symmetric inside the patient.
Of course, I understand that some departments have ring applicators that they absolutely need to use to treat their patients. And as much as I recommend only treating patients using the applicator model, if this is not an option for you, there is an alternative besides using two separate treatment plans. This is because a lot of these source position differences make minimal difference clinically. And this is because the clinical region that we're interested in lies quite a way away from the dwell positions. So small differences in dwell positions at a distance can make not so much difference clinically, particularly if you're looking at things like the high-risk CTV, D90 dose, or the bladder D2cc doses. The difference between right and wrong dwell positions in some of these cases is actually really small. So a simple solution that you could use if you had no other option but to treat with a ring applicator without the applicator model is to choose an offset that best matches the clinical dwell positions that you need and also keeps the differences between the clinical and the plan dwell positions within a tolerance of around about 2 millimeters. So in the case that we've been looking at in the past few slides, my choice would be to use an offset of 2 millimeters that keeps our planned dwell positions relatively close to what our actual dwell positions should be.
If you remember from Ben's presentation yesterday about step backward systems, he had a nice fluctuation of offsets for each dwell position as well. If you remember that plot of angle versus offset. So that was also within plus or minus 2 millimeters. So this is a very good approach if you don't have a library.
Obviously, I want to spread a big word of caution. So even if your department has the Electa applicator library and the applicator model for your particular ring applicator system, you must always verify the source path for your particular applicator and for your source and afterloader as part of the applicator commissioning. The applicator model that is created by Electa is a generic applicator model, and you may find that your particular applicator does not meet the model requirements that Electa provides. In these cases, if you can give enough data and measurements to the Electa company, they can create a customized individual model that suits your particular department. All applicators and sources and afterloaders will behave slightly differently to each other. So I cannot stress enough that it's important that you match and you make sure that your system is validated for the Electa applicator model.
Okay, and she's listed her references here as well. And again, if you have any questions, you can email Claire directly. I am also available to answer the questions. So I think this is a good time to take a few minutes to answer any questions about stepping forward systems. If you guys want to type them in, I'll be happy to answer them to the best of my ability.
Everyone's welcome to speak right now. Are there any questions right now? Okay, I didn't hear any questions, but if anyone does have a question, you can just type in the chat box, I have a question, or you can type what your question is, okay? And then with that, it seems like Claire's videos were very clear, and I certainly appreciated them. We will have this available after the presentation to share with you guys. Oh, here's a question from, a comment from Michael. Claire showed an autoradiograph on graphchromic film of the ring and dwell positions. It would be nice to know her settings for acquiring the image.
I will ask her. I'd like to know that as well. So I'm not sure. I'm not sure that it would have been graphchromic film. I'll have to check into that, because to my knowledge, I've never been able to use graphchromic film due to the nature of the film, that it's meant for higher doses and typically megavoltage machines. If it was indeed graphchromic film, I would be just as curious to know how. So I'll ask her and I'll send that information. If it is graphchromic information, then we'll forward that information to the group. Good question, Michael. Okay, so hopefully my presentation will be as clear as Claire's. I'll be talking about backward stepping HDR afterloaders. I've got a lot of information, so I'll try and go as quickly as possible while still maintaining clarity in the presentation. Again, here's my email address. If you have questions, you can email me after the presentation. Okay, so stepping backwards, these are typically Varian or Babig afterloaders. What does that mean? Basically, the source starts at the distal end of the applicator and moves backward towards the machine. Okay, why is the ring different? Just a recap from Claire. The source travels along this. I won't recap this. This is all stuff that Claire talked about, why rings are different. What are the differences for backward stepping sources? The source is driven all the way to the end of the ring. The source is retracted backward for treatment. The source cable straightens and tightens the wire over the first few millimeters of retraction, and the source does not actually move. Okay, so if you think about a kid playing with a rope outside, she puts the rope loosely around a tree trunk, a few centimeters gap all the way around this tree trunk. If she pulls on the rope, what happens? Well, intuitively, first, the rope tightens around the tree, and then the rope pulls back to her. So if you think about a real world sort of example, it makes a little bit more sense. I'll show you pictures to elaborate on the ring system. Once the cable is tight, the source stepping motion is generally uniform. So here are a bunch of x-rays of a dummy inside a ring, and you can see the motion being stepped backwards. So if we look at a zoom up in a gamma med system, the two furthest sources, the two furthest dwell positions for a 5 millimeter step size, 1300 millimeters and 1295, I've zoomed up on these two images. So here you see the end of the dummy in the 1300. Here's the end of the dummy in the 1295. A 5 millimeter step size, yet it only moved 2 millimeters backwards. So this is that tightening first without much motion of the actual source itself. Okay, so again, here are pictures at 5 different dwell positions, 5 millimeter spacing. And if we look at the actual source wire, and look how close it is to the edge of the ring. Now you look at it at 1295, hold back 5 millimeters, it's tightened. You can see visually that it's tightened around the inner lumen of the ring. And what that means is, we draw the same line, and you look at the tip of the source is barely moved from 1300 to 1295. And that's because most of the motion went into those green arrows where it's just tightened around the ring without actually moving the source backwards. So this is a very important concept for stepping backward systems. And then after that, you can see that same red line drawn. And now you can see with a 5 millimeter step, it's moved 5 millimeters backwards. The next one, another 5 millimeters. The next one, another 5 millimeters. So you can see this with backward stepping sources. The problems exist at the distal end of the dwell positions where that tightening occurs. And once the tightening has occurred, then you have basically uniform step motions after that, which is a lot different than the forward stepping systems. Again, a picture. So here's the red. Just to reiterate again, the red line represents the 1300 millimeter with a little active source there. The blue line is 5 millimeter step backwards. And I've exaggerated the fact that there's a 5 millimeter step size, yet the source is barely moving. And I've exaggerated the source tightening along the wire. And then you can see uniform step sizes after that. Okay, so this is the main process of backward stepping systems that you must understand. Is this the same for all ring applicators and afterloaders? So as Claire presented in her presentation, no, it's not. So she eloquently explained some of the reasons in forward stepping, similar reasons for backward stepping. I won't go into as much detail for her, but you must understand that each applicator behaves differently. They behave differently for different sizes, for different afterloaders. All these different things affect the source path in your ring. So you have to commission it for your ring and your applicator and each individual ring. So even if I get 2 of the same rings from the vendor, I have to commission each one because they could still be different from each other. Here's just an example of 2 different rings from Varian. And you can see one is less than 360 degrees. One goes all the way around, and some it's more than 360 degrees. All these different things factor into how your source behaves. Okay, so now that we understand what is happening, how do we commission it? So this is important. So these same commissioning procedures can be used in stepping forward systems or stepping backward systems. This is really elaborating on the actual commissioning process. Claire explained what's happening in the stepping forward systems and how you can correct for it on your planning system. And I've explained what's happening in your stepping backward systems. I will explain what to do in your treatment planning system. But now we need to know how to commission both of them. So I'll give you 2 examples, one using autoradiographs, the other using an X-ray source and dummy sources. And you should use both options. So on one ring, you should use autoradiographs, and you should use the X-ray method. They should both agree. If they do not agree, then you should repeat results until they do agree. Okay, two separate methods should arrive at the same result for the same mechanical system. Okay, so in a lot of rings, you can't see the end of the ring. Some you can, some you can't. But let's assume in this example that you cannot see the end of the ring, or whatever the case is. You can use solid model applicator files, if you have them, to allow you to reconstruct the inner geometry relative to the outer geometry. So if you can see the outside of the ring, if your ring is set up like that, then it becomes easier. You can see the end of the actual ring applicator itself. You can take data from your manufacturer, see that dead space, as Ben was discussing last time, and then you can find that the physical position of the first dwell position in your treatment planning system. Okay, if you can't see the end of the ring, it becomes more difficult. So my rings, for example, I cannot see the end. So then you have to use whatever method you have to ensure that you know exactly where the end of the inner lumen is and where that first dwell position will be in your treatment planning system upon reconstruction. So there are multiple ways to find this. One is solid model applicator files. If you have these, use them. So if you take an X-ray, for example, like I've got here, I can easily overlay my solid model applicator on there, and I can quickly and easily, you can see my mouse, my solid model applicator file will show me where the first dwell position is, and there we go. I know what it is in treatment planning, and then when I take my measurements and see where that is, I can correlate the two and see where the offsets are between each source position, here, 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 so on, as Claire discussed. Okay, if you don't have solid model applicator files, you can get documents from your vendors. So your vendors should always be able to specify exactly what the inner geometry is relative to the outer geometry. They should be able to specify exactly where the first dwell position is based on a particular reconstruction. And so lots of times they may specify by an angle relative to basically this handle of the ring. So the ring is coming in here and then going around. They may specify an exact angle from the center of the ring over to either where the end of the inner lumen is or to where the first position is. You can get this data from the vendors. Okay, so by one method or the other, you have to know relative to outer geometry and relative to your reconstruction method where that first dwell position is. You can get that through applicator files or through vendor documents, but you have to know that. So now I'll describe autoradiographs first, because that's what we're most used to with applicator commissioning. So again, you have to know the outer geometry relative to the inner geometry. So in this case, I'm using solid applicator files. I could just as well use some angle provided by the vendor in vendor documents. Okay, so in this autoradiographs, you have to be very careful about taping the ring to the film to ensure proper alignment and rotation. So if you've got a slight rotation, that can cause large errors in your source positioning. So be really careful. So I took vendor models. So in my particular ring, I have a little notch here and a little notch here. According to the vendor documents, this exact angle was 120 degrees. So I did that exactly on a film with a protractor. I then measured in a vendor document exactly the length of this line back here. And I drew that line exactly in the position laterally and longitudinally. And that way, when I draw this on film exactly to vendor specifications, I can carefully put the applicator in the exact right placement and then carefully tape it down, and I'm ready to go. The geometry is perfect. I know where my first source is by the vendor specifications, either in documents or applicator models. And I've taped it down in perfect geometry externally as well. So I'm ready to take my autoradiographs. Also important to note, you must not have any gaps between the surface of this applicator and the film itself. So be really careful that there are no gaps. Tape it down tightly. Again, this is a GammaMed IX Plus example, as you'll see in a lot of these, because that's what I have, but I'm teaching the techniques of how to do something, so it's easy to translate what I'm telling you to your own system. But just to note that a lot of these are for GammaMed IX examples that you're actually looking at. Okay, you want to ensure that the transfer tube is as straight as possible during commissioning. So when you're setting this up to take your autoradiograph, don't have large bends in your transfer tube. Okay, that's important. That can change the actual physical position when it enters the ring or any applicator. So note that this is important for all applicators. When you're commissioning any applicator, make sure the transfer tube is straight, because that could change the positioning. And if we're noting that it's changing the position in commissioning, do it for treatments as well. Okay, that's important. So if your commissions don't have them bending all over the place, hook them up straight as well, because you want your clinical scenario to be as close as possible to your commissioning scenario. So now we look at what the autoradiographs actually look like. Okay, so I've done autoradiographs twice for each applicator. And then I'll again do the next commissioning process using x-rays for each applicator. And all three examples should agree with each other. All right, the more results that you do, they should all agree. And you should be more confident when you have more results and more methods that all show the same answer. So I've done 2 autoradiographs for each ring. And this confirms uncertainties due to alignment and my own positioning in the film, and also ensures systematic motion of the source. So it's a good thing to run it twice. Note that I've drawn lines through each of these dwell positions, and I'll show you how we can relate this to the treatment planning system dwell positions in a couple slides from now. Right now, I'll just show you one little trick for actually drawing through the center of the ring. So notice I've got lots of dwell positions here. And if you're trying to draw a straight line through these and get an exact degree angle, it can be a little bit tricky. So I'm going to show you a little trick here.
Okay, so I've got a film I've just drawn on, but we're assuming that I put, say, a tandem down, drawn the tip of the tandem, made one exposure, and I've drawn in pen, but this represents an exposure. So it's just a trick of how to find the center of the exposure. So if I put a ruler down, I try and draw the center, I've blocked half of this little exposure, so I don't know if I'm in the center, if I'm 1 millimeter towards the distal end of the applicator, if I'm 1 millimeter too shallow. It's tough to tell because the ruler is covering half of it. So just a little quick tip. Draw on a piece of paper below it, a straight line. And now you can take this and you can move this film around and find exactly where you think is the center of this exposure. Draw a little point on each side of the film, and now you can move it and just use your ruler to draw a straight line through those 2 points, and there we go. We found the center of the source, and this works very well with the ring commissioning, where it's very difficult to sort of find these. That's just a little trick for finding the center of the active dwell position.
Okay, so now that we've drawn these lines through the center of our dwell positions, we want to correlate that to the treatment planning system. So, like I said before, either through your library applicators or in your vendor documents, they can give you, specify in one way or another, the exact angle relative to something where each dwell position should be in your treatment planning system based on a particular reconstruction. Okay, and now we've just done the same thing with our film. So if you look at this diagram, here's our ring. This is our source, this black line. The source wire comes in, moves around, and here's where we've measured it. Let's say this is through one of our spots irradiated on the film, and we've measured it here. Our TPS from our vendor documents or our applicator files says the angle should be this. Okay, so it's saying the angle should be alpha, but we actually measured theta, So the difference between the two angles is theta minus alpha. And it becomes quite simple. So R, this here, R, is your radius of your path that the source takes. So basically, that's your ring diameter. A 30 millimeter ring, R would be 1.5 cm. And then arc length, S equals R times angle, radius times the angle that the arc extends through. Simple equation. And so if our radius is R, and the difference between measured and the treatment planning system is theta minus alpha, this delta S, the difference in arc length, simply equals the radius of your ring times the difference of the two angles measured and from your TPS or your document or your solid model applicators. All right. So it's a very simple approach, and this delta S is basically this difference between your measured and your TPS dwell positions, as Claire was discussing in the last presentation. So here, this spreadsheet that we've given you. So again, I urge you to use these spreadsheets and to ask us questions as you use them. We'll be happy to answer. And you can see here's I got from our solid model applicator files. As easy as that. Solid model, and just take the angles on our TPS. And I found the exact degrees that it should be for these dwell positions. Then I measured on the film. I drew those lines through each autoradiograph dwell position, and I got the degrees on my film. From that, I'm able to calculate arc length for each one. The source position measures treatment planning. And noting in my example here, the vendor documents specified from this 0 degrees horizontal going counterclockwise for the direction. So that's how I specified my angles as well. Again, this will depend on how your vendor, you can recreate the concepts without following exactly what I did. So with your particular treatment planning system, your documents, your applicators. But from this, you can see, since I'm going from 0 degrees this way, film minus TPS, I've got these minuses. You can see the arc length for TPS is bigger than the arc length measured, which makes sense. It means my measured dwell positions are closer to the tip than my treatment planning dwell positions, right? Because the whole explanation at the beginning, where those first few dwell positions don't move, and then it moves in equal step sizes. Okay, so these are my offsets for each individual dwell position for my particular applicator. And you can see that I got the exact same average result for both of them. And these are plus or minus less than 2 millimeters from each individual step size, the average. Okay, so now we go to a different process of commissioning. We're going to use our X-ray to commission our applicators. We X-ray the dummy source in the machine and not a marker wire that you use for simulation of the patient to verify channel number, source positioning. Okay, that's important. The dummy source uses the same cable as the active source, but the marker wires used for simulation may or may not, and most likely do not. This, as stated earlier, can change how the source moves in the ring. So do not use marker wires that you use for simulation. Use the dummy source in your actual afterloader. You can use radiographic film with a processor, or you can use a digital radiograph. Again, this goes back to Michael's question. So if Claire indeed used gaphchromic film, which I'm not aware of, she can explain to us all how it's done. To my knowledge, I haven't seen it done before. So again, we'll answer that question if it is possible. But to my knowledge, the best options are radiographic film with film processor or a digital radiograph. Okay, so first we note that we are commissioning the active dwell positions, but we're using a dummy source. These are not the same things. So in order to commission the active source, what we're using for treatments, who cares what the dummy source is doing if the active source is behaving much differently. Okay? So we're commissioning the active source, but we're using a dummy source to do this. So we must measure the dwell positions of both in your QA device and correlate any systematic offsets. Okay, that's very important. So I've set up my daily QA device. You may have a different one. The process is the same. Notice I've got a straight transfer tube, as I do with all of my measurements. So if we zoom up on the measurements, here we have the active source, which you don't have to realize what the measurements are, but for the Gamma Med system, this is spot on. It's a perfect measurement. It's exactly where it's supposed to be. For the dummy source, however, you can see the end of the dummy source at this red line and the end of the active source here. The dummy source is 1 millimeter too short. So we have a systematic offset between our dummy source in my clinic and the active source. So we need to take this into consideration when we're doing our commissioning. I'll elaborate on this in further slides. So when we x-ray the dummy source, here we've got the portable x-ray machine. I've got my afterloader here connected to my ring, taped down to the detector for the portable x-ray. Again, straight transfer tube in all measurements. We'll center the detector, center the ring on the detector. Again, no gap between the ring and the detector. We want no divergence. We want a perfect orthogonal image for our applicator, so make sure that all your devices, each angle on this side and the other side, are set to 0 degrees. We want a large SSD. There is a tiny bit of magnification because the actual source itself is a few millimeters away from the detector. So if you brought your X-ray tube right on top of the ring, then you actually have some issues with magnification. So just make the SSD relatively large. You'll have no problems with magnification at all. And here's a perfect setup here. Now that we've set it up, we'll take some images. Again, you want your lowest KV possible. This accentuates the photoelectric effect and the differences in effective atomic number between your different media here. And you don't need much MAS. I have 1.1 MAS, 40 kVp. I'm getting great images. Okay, so I can see my dummy source perfectly. These are the images I showed earlier in the presentation. Now we need to relate the position of the dummy to the center of the active source. Okay, so I'm using, again, the Varian Gamma Med IX Plus example. So this is an example of how I'm doing it. But again, it's super easy for you to do it in your own system based on these same techniques. The process is the exact same, you just have slightly different values. And we'll give you some documents where you can actually ensure that you're using the correct values. So in the Gamma Med IX Plus, here's my dummy wire. The source is connected, welded at the end of the wire. Here's my active source in red. This is encapsulation, and it just so happens in my particular system, from the end of the active source to the center, from the end of the wire, everything, to the center of the active source is exactly 2.5 millimeters in my system. It'll be slightly different for yours, possibly, but the process is the same. So that being said, on my system, here's 2.5 millimeters from the end of my dummy. This should be the center of the active source, right? No. Remember, we measured our dummy source 1 millimeter shorter than our active source in my situation. That means that in my particular situation that I'm explaining here, the center of the active source would only be 1.5 millimeters shy of the end of our dummy wire. So that's the importance of correlating any systematic differences between length of your dummy and length of your active source. We're commissioning our active source based on position of a dummy source. That's an important concept to understand. Okay, so now you can overlay your solid applicator models on your X-ray images in your TPS and directly find the offsets for every position relative to the dwell position visualized in your TPS. Likewise, you could do a similar thing with angles. So I could measure all the angles on my digital radiographs, and I can compare them to the measured angles based on vendor documentation, as I did with my autoradiographs. Either option is perfectly valid. And basically, we just find those differences in distance. Okay, quite straightforward. In the applicator models, we would match our applicator model to the image, then see our source positions in the TPS invariant. Here they show up as these purple squares, rectangles, which you can just barely see. And we can directly measure the offset. Again, we could also use the angular measurements as I described in the autoradiograph section. Okay, so here's another table in that same Excel sheet. So the first table explained using angular measurements. This table explains using just measurements to solid applicator models. So here's another table that we can fill out. This is what I've done here. And if you remember from our TPS, I got for this applicator minus 5.4 twice. And with the digital radiograph, I got minus 5.4 and minus 4.6. Okay, so from all four of these measurements, I've decided for this particular ring in my system to use a minus 5 millimeter offset. That means that the delivered positions are actually 5 millimeters closer to the tip of the tip of the applicator than my treatment planning system. And note again that all of these are within plus or minus 1.5 millimeters. As explained, is one possibility to use in step forward systems, and was explained in Ben's presentation yesterday that you will get this fluctuation about the average. Verification. This is extremely important. So after obtaining this offset value, the shift toward the tip that accounts for the differences between measured TPS and measured and TPS dwell positions, we must verify that this is correct. So you have to deliver a plan with symmetric ovoid light loading with this shift applied and verify in an autoradiograph that we have a symmetric delivery. Okay, so we want to ensure that this offset is correct. So you have to ensure this with a film delivery. So here's our symmetric dosimetry plan. And I've got the applicator reconstructed properly here. So the arrow being the first reconstruction point at the tip at this end of the internal lumen. Note that in this particular applicator, we have a slight dip in the isodose lines, and that's just because on this particular applicator, maybe not yours, dwell positions are actually exiting this plane. Okay, so that's why it looks a little bit weird on my system. And what we would do is, here are the sources shifted by that 5 millimeters in my system. And we note that when we deliver this in my system on my ring, based on the previous examples, that delivered, they should be 5 millimeters closer to the distal end. That's what we commissioned. So when I actually delivered it, here they go. Here's my film, perfectly symmetric here, perfectly symmetric here. Again, here's that dip in isodose as explained here on this slide. Okay, so you always want to verify whatever method. I'll show you one other method for correcting in a couple slides. Whatever method you have for correcting, whatever you're going to use for your patient delivery, you have to do an autoradiograph to show that if you think, based on your system of delivery, that you're going to give a symmetric plan, you must verify that it is a symmetric plan on an autoradiograph by whichever the two methods that I'm going to explain to you now. So here's how you can fix this offset issue in backward stepping systems. We have two methods. First is you can extend your initial reconstruction point of your applicator further towards or past the end of your ring applicator by the amount of offset determined during commissioning. This is what Claire alluded to previously and what Ben briefly spoke about yesterday. Okay, but you have to be a little bit careful because if you're using applicator models, now if you're shifting the first reconstruction point further past that inner lumen, then your solid applicator models will now no longer match by that same amount. Okay, so there is a little bit of a risk there. So here's what I mean. So here is the original reconstruction point for a variant system, and they've commissioned it, and they've decided to put their first reconstruction point shifted beyond the inner lumen by the amount determined in commissioning. Again, this distance is the offset between measured and TPS dwell positions. So that's one method of doing it. And again, I'll just say again, we should also do a verification plan by this method, delivering symmetric sources in the TPS and verifying that we still get symmetric sources in the delivery to a film. Okay, I'm going to show you a quick video that explains both methods.
Okay, so here we want to discuss the two methods for correcting for a backward stepping system like in the variant unit. So here I've got a ring, and you can see there's an arrow right here indicating on my planning system that the first reconstruction point is here. You can see the first reconstruction point is at the end of the internal lumen. So it's been reconstructed properly. So if I load on this planning system, dwell positions, symmetric, notice there's a slight dip here due to the fact that sources are leaving this plane, as discussed on the PowerPoint presentation. So I load symmetrically. But as we remember, when we commissioned, we saw that the measured dwell positions in our system were 5 millimeters closer to the tip than the actual dwell positions. So if these are my dwell positions on the patient's right or the screen's left side, then when this is actually in the patient, it would look like this, the isodose lines, and the actual dwell positions would look like this, even though it's planned on the planning system like this, because our delivered dwell positions are shifted closer to the tip in the commissioning data that I showed by 5 millimeters. Okay, so if we want to deliver positions in the dose in the patient that looks like this, one option would be to actually shift our planned dwell positions, which are here and here, shift them around away from the inner lumen by 5 millimeters. So now instead, so here are our dwell positions originally, let's shift them away from the tip by another 5 millimeters. Okay, so now we just have new dwell positions shifted away 5 millimeters. So on our planning system, the isodose lines look like this. And still, our reconstruction point is at the internal edge of the inner lumen. So if this is what it looks like on our planning system, then on the actual patient when it's delivered, remember delivery is 5 millimeters closer to the tip, so delivery looks like this as we want it. So the first option is to do a dosimetry plan, which looks like we want it, and then to copy and paste the plan, make it a delivery plan, shift the dwell positions away from the distal end by the offset determined in commissioning. So a new delivery plan looks like this, but it delivers inside the patient like this. So that's one option. Another option is if we know we want our dwell positions on the planning system to look like this in order to deliver in the patient, which looks like this, then we can do a trick. So here's where we want it in the planning system in order to deliver it symmetrically. And notice our dwell first reconstruction point is here. So if we do a trick and we shift this first reconstruction point by that offset determined in commissioning, so in this case it was 5 millimeters, We shift it 5 millimeters. Now look, we have a symmetric distribution once again. So this is the other option. These are the actual delivery positions, which will in turn show up correctly on your planning system because we've planned with our first reconstruction point shifted past the internal lumen by the amount that we discovered in commissioning. And this amount is the difference between the measured dwell positions and the actual dwell positions in the TPS. So by this method, if you reconstruct here, then what you deliver is actually shows up the same as what you do on your treatment planning system.
Okay, so this is a very confusing thing for everybody, no matter how experienced you are as a physicist. So again, I strongly urge that whichever approach you take, you run your delivery plan. So you make a plan that you think in a patient will be symmetric. Whichever method you choose, run that plan in your applicator with film attached to it and make sure that it is indeed symmetric on your film. Okay, so that's the best way to ensure that there's no confusion that you've done it properly. Okay, so again, this is just reiterating what I've already explained in that video. So important note, you cannot use any sources during the tightening phase of the dwell positions. So in those first couple dwell positions, in my case between 1300 and 1295, where it was just tightening around the inner ring and the source wasn't moving, you can't use dwell positions during this tightening phase. Because during this time, the actual step sizes do not agree with the step sizes in the TPS. So only if your vendor supplies a TPS applicator model with the variable step sizes built into the source position, you can use these dwell positions, like a Newcastle, for example. The dwell positions that you cannot use in treatment planning are usually somewhere between a few millimeters up to 5 or 6 millimeters less than the maximum allowable dwell position in your TPS. The exact value is determined during commissioning. So in this particular example, and on this ring in my clinic, where we have a maximum dwell position of 1300, I do not allow our physicists to plan using any dwell positions higher than 1295 in my planning system. So again, this is something that you will find out, which will be vendor, machine, and applicator specific, but very important as well. And again, here are a couple references, and I think it's time for questions.
Adam, thank you so much for that wonderful presentation. That was really good. During your presentation, there were many participants who said that this was very clear, and if possible, they would like a video of this recording. And so our Rayos Contra Cancer team will make a video from the session today, and we'll be sure to share it with everyone. We have the email contacts of the primary clinic coordinator at each of your centers. However, if you haven't been getting the lecture schedules or the presentations or the previous recordings, please type to everyone your email in the chat, and so we can make sure that we get the presentation materials to you also. You can also email our team at info@rayoscontracancer.org.
Okay, well, I hope it was clear and helpful for everyone. And again, I think Claire, Ben, Sanja, and myself are all excited to see some of your own ring commissioning and use of our spreadsheets. And again, we're here, our emails are here. We're happy to assist you when you actually get to it in your clinic. or even if you want to recheck what you've already done in your clinic, then we'll be happy to check any of your work or answer questions. So feel free to email us whenever. That's what we're here for.
And I do have one special announcement to make. So we have, I think, 10 different centers joining us today from different countries in Africa and Middle East, and all of you are in very exciting stages of development. Some are just beginning to commission your HDR Brachytherapy afterloaders, and some are also working on developing your linear accelerator programs. And today, August 28th, 2019, the first teletherapy patient in Maputo Hospital in Mozambique received their treatment. So congratulations to Nadine and his team for starting what I think is a great future for Mozambique.
Very good. Very exciting.
And it's wonderful to see everyone. I'm going to unmute everyone, so if anyone wants to say anything, they can, and we can adjourn the session.
Actually, Ben, I have a couple questions that were asked. I can answer them. They may be helpful for everyone else.
Sure, absolutely. Okay.
So, let's see. I've got a question. Sorry. Where is it? Is it necessary to remeasure or verify the offset for each new source exchange? No. So it's assumed that your source uses the same source wire material and construction as the previous one. So it's not necessary to redo the commissioning for that. If your applicator, if your manufacturer changes their source model, then it would be necessary, because maybe there are differences in how this new source from this manufacturer interacts with your applicator. But in case not, no. We assume that for one particular applicator, one particular machine, that the source will behave the same after a new source exchange. Good question, though. And I've got another question here. In the case you decide to fix the tightening issue by extending the applicator model in the TPS, you have to edit the model provided by the vendor. Is that okay from the responsibility point of view? Okay, so again, both methods have a risk that you need to assess as physicists. So you need to decide as physicists whether you think it's less risky to copy and paste the plan and shift the dwell positions by a known amount, or if you think it's less risky to extend the tip of the applicator beyond where it's supposed to by that offset amount. So that's up to you. So you can change the applicator model, possibly, if your vendor allows it, or you can ask your vendor to do it for you. You can create a manual ring model that you can just overlay on your applicator file by the vendor, and that way you can have it match everything in the vendor model and just extend it by your offset amount further. This is a process that needs to be discussed amongst your team and to decide which one you think is the most effective with the least chance of error. It's a very good question. Okay, that I think answers all the questions. And thank you again, everyone, for your time this evening.
Thank you.
Okay. See you all next week.
See you all. Thanks for this information.
For everyone, our next session, we're going to send out the schedule for September, and we'll also send out the tentative schedule that we have for October. But next week, we have a session on Tuesday at 8 a.m. Pacific time. So that's the same hour as what we just did. And Then we will have a session on Wednesday at 9 a.m. Pacific time, so 1 hour different. And these will be from MD Anderson Cancer Center.
And he'll be talking about treatment planning system commissioning. This is a very exciting topic, I think, for everybody.
So we will be communicating with the clinic coordinators at each of your centers. To each of you, thank you very much for sharing with the rest of the members of your clinic. And I'll try to also email the people that have provided me their email addresses. Thank you so much, everyone. Have a great rest of your day.
Bye.